some of the details of using the sinusoidal wave equation now. So one question we might ask, well, how do we tell which direction the wave is travelling from the sinusoidal wave equation? It turns out that the signs in front of the x and the t terms in the equation tell us which direction the wave's going. So when we have the equation y as a function of x and t is equal to a sine kx minus omega t plus phi, this describes a wave travelling in the positive direction. Whereas when we have the equation y of x and t is equal to a sine kx plus omega t plus phi, this describes a wave travelling in the negative direction. So the rule is, when the signs in front of the x and the t terms are opposite, the wave is going in the positive direction. When the signs are the same, the wave is going in the negative direction. Another thing we might ask is, well, how can we use this equation to calculate the speed of the wave? We've seen before that the wave speed, v, is equal to f lambda. Now, we can multiply the top and the bottom of this equation by 2 pi and end up with the same thing. So we can say that v is equal to 2 pi f times lambda divided by 2 pi. And we'd want to do this because now we can relate it to the wave number and omega. So we know that the wave number is equal to 2 pi over lambda, and this tells us that we can write 1 over k is equal to lambda over 2 pi, which is what we had in our equation for speed. So our equation for speed, we can replace the 2 pi f with omega and the lambda over 2 pi with k. So we can get the speed of the wave as omega on k. So let's have a look at an example of using this now.
So the question is, what is the speed of a wave described by the equation y of x and t is equal to 2 sine of 3x plus 2t plus 1? Is it going in a positive or negative direction? Okay, so to answer this, we'll need to use our equation v is equal to omega over k. Now, omega in this case is what's in front of the t. So omega is equal to 2, and that's in radians per second. And k, that's what's in front of the x. So that's equal to 3, and that's radians per meter. So now, substituting in, we've got 2 radians per second over 3 radians per meter. So you can see that's going to be 2/3 or 0.67 meters per second as the speed. Now ask us if it's going in the positive or the negative direction. In this case, the term in front of the x and the term in front of the t have the same sign. So this tells us that it's going in the negative direction.
Now, another thing that you may be wondering is, why did we look at simple harmonic motion and now we've come back to waves? How are these related? Well, it turns out that as a sinusoidal wave passes through a medium, the medium is moving backwards and forwards with simple harmonic motion. Okay, so let's use what we know about simple harmonic motion and what we know about waves now to show this relationship.
So what we're trying to show now is that these little green dots, if you concentrate on the little green dot for a minute, it's moving up and down in simple harmonic motion. So we know for simple harmonic motion, the displacement of a particle from its equilibrium position can be described by the equation y is equal to a cos omega t plus phi, where phi is a phase constant and it's chosen so that we can match whichever equilibrium conditions we're given. So let's just rewrite this because it'll be a bit more useful this way, as y equals a cos omega t plus phi dash. So phi dash means the same thing as phi. It's just useful to have a slightly different symbol for it, as we'll see later. Okay, now for a wave, we can assume it's going in the positive direction, like the wave you're looking at. So this is described by the equation y is equal to a sine kx minus omega t plus phi. Okay, now we can consider any point on the wave, but we're just considering one x and then looking at how the y changes at that x. So let's keep everything simple and just choose x equals 0. This is arbitrary, we could choose anything, but let's just keep the math simple. Okay, so this tells us that y is equal to a sine, now kx, that's 0, so now I've got minus omega t plus phi. Now, to get these two into the same format, we're going to need to use a little bit of trigonometry. So one rule in trigonometry is that sine of x is the same as cosine. So this is actually why it's called cosine of 90 degrees minus x. But we'll be using radians now, so we'll rewrite 90 degrees as radians. So this is cos pi on 2 minus x. Okay, so what we can do now is take this wave equation here and write it in terms of cos, because rather than having sine, so here we've got x is equal to minus omega t plus phi, and we substitute this in now as y is equal to a. Okay, so now we've got cos of pi on 2 minus omega t plus phi. So we've just combined this expression with this one now. So we can write this as a cos omega t, because we've got minus, so that gives us omega t. And then we've got this plus pi on 2, and then we've got minus phi. Now, phi and phi dash can really be anything. They're just there to match our starting conditions. So we can let phi dash equal pi on 2 minus phi. And then we've got that for our wave, y is equal to a cos omega t plus phi dash to describe how the height at a fixed x changes. So the height at a fixed x changes in a way that's consistent with simple harmonic motion. So it's undergoing simple harmonic motion with the same amplitude a as the wave.